Out. Hi, everyone. Welcome to Working Group Serving multi-host Workstream meeting. In today's session, we invite Abdullah, the maintainer of the leader worker set, to give us a deep dive session on it. Leader worker set is a deployment API that addresses common deployment patterns of AI inference workloads, especially multi-hosted inference workloads where the LLM can be shared and run across devices. Yeah, Abdullah, I'll hand over to you.
Just a second. All right, yeah. Thank you, Jashin. Yeah, my name is Abdullah. I'm co-chair 6 scheduling. I've been involved with working group batch and now with work group serving. So today I'm going to present why we developed like this new API that we're calling leader worker set, the use case and the mechanics, how it works. So let's start with the problem. I only have 3 slides. The hope here is that we have an interactive discussion. So the main problem we're trying to solve here is that recently model sizes are continuously growing. We have Llama 7B, Llama 70B, but now like Llama 3 is now going into like 400 billion parameters. The issue here is that those models at some point are not going to fit into the accelerators of a single node. Usually, as we discussed previously, all of these like LLM models, they require accelerators, GPUs or TPUs. GPUs or TPUs memory, like accelerated memory is limited per device. You can find like, maybe 20, 40 gigabytes of memory per device. Most cases, you can find probably up to 8 GPUs, for example, 8 devices in a single machine. So that like is not enough to host some of these large models. And so the only way to serve such large models is that they need to be sharded across multiple nodes. And so we're moving from multi-GPU. So like we started with the smaller models, they fit on a single GPU, they got larger. Now we're using multiple GPUs in a single node, but now they are becoming much larger that the GPUs of a single node don't fit. And now we're sharding across the GPUs, across nodes as well. And so in reality, the model server, instead of basically a process that is running on a node, it's becoming a distributed job, like a distributed server, distributed model server that needs to run on a group of nodes. Now, to reduce network overheads, like, okay, within a single node, usually GPUs, they have NVLinks and sharding between the node, between the GPUs, and communication is not a significant deal. But once we go multi-node, the network overhead, when we're doing, for example, like if we're doing sharding, you do some sort of like collective communication, you're doing all reduce and such, becomes a problem. And so another requirement here is not just that we want the mechanics to shard the model across multiple nodes, but also make sure that those nodes are co-located. So you can imagine like within a single, the same rack, and if you're familiar with TPUs, within the same TPU pod. Usually the group size is fixed. What I mean by that is, like, the model size. For example, it's a Llama 3 400 gigabyte, right? 400 billion parameters. You would probably need maybe two nodes. We're not going to auto scale the size of that group. Same thing like when you use, for example, like Llama 7B or Llama 70B, you decide, oh, I need 2 A100 GPUs, for example. You're not going to scale the number of GPUs at runtime. You may want to use less GPUs if you're doing quantization, but you're not doing it at runtime. So basically, when you deploy, the size of the group. So the group size is fixed to support a single, distributed model server. However, you will want to horizontally scale the number of those like groups. So that is another requirement here. So just quickly to recap, model sizes are getting larger and larger. They don't fit the GPU memory that you can aggregate on a single node, and so you need to aggregate across multiple nodes. You want the mechanics to be able, like, create a group of nodes as a unit, so that you're able to deploy those distributed model servers. There is the characteristic of these groups usually is fixed, but you need to auto scale the number of groups. Any questions up to this point? Does this make sense? Is this a problem that resonates with what you observe in practice in your deployments? Any questions so far? Okay. Moving on, so this is the problem we're trying to solve. And when we deploy this in Kubernetes, like when you deploy deployments in Kubernetes, you usually use the deployment, right? And a deployment, basically, it creates a number of replicas, and each replica is assumed to be your model server. Now, in this case, as I mentioned, your replica is not a single pod. Your replica is basically a group of pods. And that's why we developed the leader worker set API, basically to give the deployment semantics, but your replica is not a single pod. Your replica is a group of pods that are that form your scaling unit. So here is like a conceptual view of the leader worker set API. So this is a custom resource that we developed. It has a number of characteristics that we basically landed on based on our experience with how usually LLM servers are developed for multi-host serving. That includes VLLM and a bunch of and SaxML, which is like an open source Google multi-host server, and other multi-host servers that we have internally at Google. So as I mentioned, like, your replica is basically a group. The group here, we've identified the need that the group of pods are not going to be completely homogeneous. Like you need at least one pod that we're calling it a leader, that you might want to have slightly different configuration for it. And so we just to basically strike this balance between what is actually needed and continuing to have a simplified, API. We've made a decision to have strictly one leader, because this is in practice what you all need, what you need. So that leader is basically, and that's why, like, you see the second bullet here, it's basically dual template group. So you have one pod, the leader, with you can configure it with a template, and the rest of the pods, the workers, they can have a different template. The power of this is, as I mentioned, you can set different resources for that leader pod. You can even use a different container, and I'll show an example of this in the next slide. The other thing here is that, as you see here, like, you have these groups, but within each group, in order to do distributed computing, whether you're doing it using MPI or you're doing it using Gray or some, like, any like, collective communication framework, it will require some sort of, like, pod identity, so that you're able to implement this sharding. Like with distributed PyTorch, you have to set the rank, the world size, and so on and so forth. So you will have local indices for these pods. So the leader is going to get index 0. The workers will get the rest, like 1, 2, etc. So in this group, this is a group of 3. This is 0, 1, 2. This is 0, 1, 2, 0, 1, 2. Like in each within group, right? Like they have local indices. Now the groups themselves will have also an index. Like this is collectively group 0, group 1, group 2, group 3. Any questions so far about the semantics of what we're trying to develop here? And please feel free to interrupt me if you have any questions at any moment.
Abdullah, other resources for resource templates for leader pod and other worker pods, can they be separated? Just like MPI job, the launcher pod and worker pod?
Exactly. So here, like, basically each of your groups is going to be an MPI job.
Okay.
So like, for example, with TensorRT, I think they have a version where you can deploy the server as an MPI job to do distributed, to do a multi-host serving. So each of these groups is going to be an MPI job, and the leader is going to have rank 0 here, rank 0 here, rank 0 here, rank 0 here, right? They are independent. They are completely independent, those groups. But within the group, right, the pods need to know each other. So we have these NDCs, and the leader here has a different template. It's exactly right. Like, you can run the driver, and then those are the workers that will basically be managed by the leader.
Got it. And as for the implementation, what's being used underneath? I don't think it's using MPI job, right? It's just using native
Exactly.
subjects.
You're exactly right. So the implementation is as described here. So the leaders are managed by a stateful set. So we create a stateful set. We call it the leader's stateful set. So basically, when you create an LWS, the first thing we do, like in a deployment, when you create a deployment and say, okay, I need 5 pods, the deployment will create a replica set, and the replica set will create 5 pods, right? When you create an LWS, the first thing that we will do, we will create a stateful set. That stateful set will represent the leaders. So this stateful set will manage these pods, the leader pods that I'm like the ones at the top. Now, for each pod that gets created by this leader stateful set, we have a watch, and that watch will basically react by creating a stateful set that is owned by these pods. So you will have another stateful set per group. And so in this example, you have 4 groups. You're going to end up with 5 stateful sets, one that manages the leaders and one that manages the rest of the workers of each group.
Thanks.
Abdullah, I think, yeah, this is kind of straightforward on the, this diagram concentrate more on the real deployment typologies, right? I think technically it's a m times n orchestration. If there's a corresponding logical view, that would be better, I think. Yeah.
Okay, I just want to respond to if there's any the questions about the implementation details. I'm gonna quickly go through this. We have a scale sub resource that allows you to scale up and down the number of groups. It supports rolling updates. Again, same thing as deployment semantics, basically as a number of groups, not within a group. And you will want some sort of group restart for failure handling, right? Because for example, if you're using MPI, you're going to have to basically, if any pod fails within the group, you need to restart everybody else. So we were providing those semantics as well. Okay, so yeah. Go ahead, sorry.
So sorry, yeah, one quick question. If we use the stateful set as underneath a workload here, so any user concerns about the upgrade speed? Because those pods we need to once it's fully deleted, we can create a new one, right? Is that I'm not sure any users have the questions on the upgrade speed.
Well, I mean, even in deployments, when you update, you have to recreate the pods.
Right. But we don't necessarily need to wait for the the one to be fully deleted, and then we can recreate the new one, right? That's a minor difference.
Yeah, I think we would use the parallel deployment strategy almost always in this. This is effectively a stateless workload using a stateful set, and the naming. Abdullah and I have chatted about this a little bit, is when we were talking about some of the design elements here. Really, the difference between replica set is you guarantee at least one of every replica, which means that there are plenty of times when you actually have more replicas than you need. The controller doesn't wait for things to be terminated to go create more. And that doesn't really work with ranking. So ranks or indexes just don't really work with that, because the specific guarantee that a stateful set provides is there's exactly one with that name, which ties to the pod. There's only one pod with a given name running on the cluster at a time. In practice, I think what you're getting at is there are workloads that want indices that in general don't need the safety properties that stateful set upgrades give. And if the current parallel update strategy isn't good enough, I actually think there's probably room for us to argue the way that people are using stateful sets is as a primitive to give them indices generally. And the upgrade and the safety aspects are kind of orthogonal to that. So I think there's an argument here that if the parallel strategy doesn't work for updates, or the parallel policy doesn't work for updates, that we should improve it. And I think that's a risk point in using stateful sets, but it's a risk that other workloads have that are using stateful sets today that aren't using leader worker set.
Yeah, makes sense. Thank you.
Yeah, I mean, that's exactly right. Like the main thing that we want to maintain here is the indices and the identities, and those are going to be tricky to deal with when, like, compared to deployments where like pods don't have identity, and so you have more flexibility in doing parallel creation. But still here, like what we're doing, for example, you could have max search. We basically increase the range of the number of, so that like, you have that illusion that you're able to do create like extra replicas while you're updating the existing ones, and then you scale them down to the exact number when the low rank replicas are updated. Matthew?
Hi, yes. So when you write that you need to ensure that replicas land on the same accelerator island, does that happen via the usual Kubernetes mechanism, such as labeling nodes and using node selector? And if so, what are sort of is there some guidelines for, say, the cluster administrator on how to label nodes? Like, are there standard labels or?
This is a great question. So the way we're doing it, like LWS is not a scheduler. It's only like what we do is we inject pod affinity and anti-affinity constraints that implements the semantic exclusivity per group. Now, that's the nice thing about it. You don't really need to know the node labels. Like you don't need to inject the node selectors. You're not selecting this for each group specifically. It is like pod affinity and anti-affinity for a generic topology. And so what you would want to basically identify is what is your grouping domain, for example, a rack. And then the assumption here is that you're going to set up your infrastructure so that each group of nodes that you want to land, where you want to collocate a group on, they share the same rack ID, right? So, and that is, but like when you deploy the LWS, you don't need to know the rack IDs themselves. You just need to tell me group by rack ID, right? So for example, on GKE, on GCP, we have what we call like TPU slices. I'm not sure if you're familiar with this. Basically, a group of nodes, they form a single, like, they are connected with like ICI, like high-speed interconnects, like fiber optics. When we provision them as a unit, right? So those four nodes, and when we provision them, they are provisioned with an ID already. It's called like the slice ID. So it's part of your infrastructure. I assume that like when NVIDIA comes out with their like similar designs, it's going to be the same thing, because by design, those hardware, they're typically, again, like all or nothing, provisioned and deprovisioned, because they also need to handle failure semantics. If one of the nodes are down, they need to bring the whole thing down. Now, even in cases where like the nodes are connected with data center networking, you still want to have network efficiencies. And so you want to bubble up the network topology, and you want to group by that as well.
So a sort of cluster administrator would have to decide what a accelerator island maps to in terms of topological element in the cluster, and make sure that the nodes have a sort of label or annotation that tracks that.
Yeah, I mean, in the most
Okay.
cruel way, it's like we right now, usually we have zone, right? So, but that is way too coarse-grained. And I assume that in, like an infrastructure, like on GKE, for example, you get the rack ID as well annotated on the nodes, like by default, or at least it's available for you to annotate on the nodes. If you get annotated, then that's it. Like with LWS, again, you don't really need to know it's rack ID, XYZ, blah, blah, blah. You just say group by rack ID, and that's it. You just need to know the key of the label, not the value.
And I want to add here
Okay,
that I think, like Matteo, that like the goal I think for serving is that we want to have a recommendation for platform admins and hardware providers and cloud providers around what the topology mechanism would be that we all as Kubernetes can agree on and how it's exposed, so that things like leader worker set, future CRDs, future orchestration can rely on that. I think that is a 100% within our charter, and the alternative would be that everybody kind of comes up with their own, which practically is just going to be annoying. So through leader worker set, through some of the other efforts for topology aware scheduling and DRA, we should be concretely coming up with use cases and saying on premise, here's what we recommend, here's what Kubernetes recommends, and if you do this, then all of these things should work with it. That doesn't really exist. We don't have a cap for topology. I think we're going to have one in a very short time. So like that's this group's, I think that's in the mission of this group, is to come up with that first very concrete use case and go seek others.
Okay, thanks very much. That was very clear.
Andre?
Hi, I just have a quick question. So can you speak a little bit about the specific indexes when it's used for model sharing? Because so from my understanding, for model training, right, like it is very important for this device placement, because you need to make sure you can quickly synchronize weights for your distributed training, because you kind of like train your model on multiple devices. So can you share a bit more from the use case perspective, like when you see the usefulness of on the serving side to have a specific device placement and assignment for the specific group of pods?
So let me go to the second slide. So that could give, like, this is the concrete example that I have that people in the community can actually go ahead and deploy. So we have other examples internal, but you can't use right now. But this one you can actually go ahead and use. You asked about like what is the concrete, like here's like you have a TPU slice. Those nodes, they form one unit, right? They're connected with like internet with ICI links. So they form a unit. And then when you create, like in this example, we're creating 10 replicas of 4 size each. This is one replica, this is second replica, and then there are 8 others. The group is going to land on one accelerator, and this group is going to form like, a distributed model server. This distributed model server is basically going to be, in this case, VLLM is going to deploy array cluster. This is array head and array workers. Those needs to know each other, right? So that it's able like to, do the distributed training. Like in case of Ray, the pod indices here don't really make a difference, because the way that Ray works is that like the Ray workers, they connect to the Ray head, right? Like, so all you need to see here, like the leader address. So those Ray workers, they only need to know the Ray head so that they register with it and things start working, right? Now, the indices and stable indices here, they lend themselves into the name of these pods. And so they provide the mechanism by which each pod will have a stable DNS name. And it helps with discovery. So this distributed model server, this group needs a mechanism by which they are able to discover each other. So the indices will provide that, because we can use them as a way to name the DNS records. Does that make sense?
So yeah, go ahead, Clayton.
I was going to actually ask, because like I heard your question also one level down, Andre, and I like want us to chat about it at least, because even on TPU, when you ask for 4 TPU nodes and the VM scheduler makes the call down to the underlying infrastructure, what's actually happening is it's making a scheduling decision into a chunk of nodes. Those chunk of nodes actually do have physical machines that are closer to each other. And one of the things that happens is when you do a 4, like this is a 4 topology, there's a, what would it be? A Dell 4x4 would be a common one. I don't know if we actually called that out in the example. That's GPU, we don't. But in a TPU example.
Yeah, V5E16, like if you
so,
look it up.
Yeah, so some of these would actually have faster, like the placement decision in the scheduler makes a decision, but some of those links take longer than others because some of those machines are physically closer or go through fewer hops. In practice, that matters the most in training because you're seeking to make sure that like the lowest latency is possible. That is something that we haven't discussed much, but my assumption would be in this model, what would kind of happen is the libraries in each worker would be looking at the physical hardware, and when they initiate the communication to the head, the process of determining like latency or, you know, like some of the libraries run self checks or latency checks. This is just to the level that you end up with things that are close, but there's still another layer down of physical topology that might actually matter for some use cases as models get bigger and bigger. We haven't really described how that would work yet. But today I assume it's a dynamic calculation that could be done in the pods, in the workers.
Yeah, that makes sense. Because like from my understanding, this could be useful when like, you know, model is too large to like serve on a single GPU. So you need to do sharding, right? Which means like when your request comes in, you need to like use multiple, you know, workers to do the prediction of the model. And I guess like from the specific use case that you're talking about here, it's because of the array architecture, right? That all the requests goes like through the head node, right? And then again, if like, you know, translate to the workers from the head node. But I'm like most speaking about like from the general serving architecture when it could be useful, this device placement and the closeness to multiple shards of your, what it is, shards of your model, or like, you know, multiple like, you know, models that you want to serve. I guess like it's just, you know, one.
So I think the assumption for this use case that we kind of have started with is effectively tensor parallelism of the model. And then, you know, in a GPU case, you're using nickel, and in a TPU case, you're using libTPU, which effectively works down. Yeah, which is basically working over the ICI protocol. And the outcome of that is, in general, there are, because of the way that tensor parallelism would work when you're sharding across multiple machines, there's several all reduced steps. And so you're still kind of each physical step of inference, at least based on my understanding, and I don't know all of the details here, but as you go through each part of the model, you're still bounded by the lowest or the highest latency between the different nodes in that calculation. So if we're just talking about inference, we're just talking about super large models, I'm sure that people will come up with ways to optimize that in the future. At least right now, my understanding is for most of the multi-host inference cases, it's not just getting the 4 so that they can, you know, figure it out across the different machines would be enough. I suspect 6 months, a year from now, we're going to be in a spot where we might actually need those details down at the lower level. But again, I think the libraries could figure it out. And I think from a Kubernetes perspective, we want to have the minimum amount of orchestration to let code go do code crazy things, because it won't just be Ray, it won't just be MPI, it won't just be nickel, it just won't be TPU, it'll be, you know, hundreds of other crazy things people come up with. We don't really want to get too far down the topology stack. That would be my opinion. I don't know if anybody has, if anything I said is wrong based on what people know, this is the forum to share it in.
Yeah, I mean, like the way that we're thinking about it at this point is that trying to provide a way for, like, for example, identities, and then leave it to the framework to decide what to do with these identities, how to shard, how to basically do the distributed computing. For the most part, as Clayton mentioned, like it's using tensor parallelism. So you can use PyTorch distributed, you can use MPI, you can use JAX, MC JAX, which is what SaxML is backed by. And all of these cases, you basically need a rank and a world size and the driver address. So, and this is basically what LWS is providing you with. Now, in the case of Ray is also kind of similar, but like we're trying to, the case here is that Ray, you actually have more flexibility with this one with Ray. You can actually create and do more than tensor parallelism. You can do disaggregated serving because the Ray workers are managed by Ray head, and you can and the process running on Ray head can use the Ray workers in any way or form or shape they want, right? And so it can get more advanced with Ray.
So,
Ravi?
quick question I had on this. You said we don't need to be aware of the hardware accelerators, and this template should be able to distribute and create your sharded pods in this case, right? But what if you have a heterogeneous like nodes where you have certain types of GPUs with different capacities, right, in your cluster, and each node, maybe multiple nodes with V100, some nodes with H100, things like that. How will, in that case, it will distribute or recognize those things?
So each group, my assumption here, each group should be homogeneous. Otherwise, I think you will find it extremely hard to implement multi-host on a heterogeneous environment, in a heterogeneous setup. Your replicas could be different, but maybe by deploying multiple LWSs. But for a single group, I would assume that they are going to be homogeneous, unless you are doing disaggregated serving, and we can get into that. But like for the tensor parallelism case, I think you will find it hard to find cases where people doing that.
Well, I think the most concrete is that I mean, I know that so nobody in cloud that I'm aware of has high-speed networking between different accelerator types. And if that's a bad assumption, let me know. So like in TPUs, at least V4, there's no V4 and V5 mixed physical infrastructures. They're just separate units. My understanding for most of the GPU generations out there across all the cloud providers is that this is the case. So you wouldn't have a high-speed networking. The multi-host use case, multi-host inference assumes high-speed networking and is not very useful without it, as Abdullah mentioned. But actually, if you have use cases that would benefit from this, that are about things in the space, that's actually part of why we're doing this, is because everybody tends to focus on massive training, and we tend to focus on the multi-host in this. That's what got us here. If there's other use cases that need groups of replicas with diverse hardware, bring them up, like point them out. And disaggregated is one that we've thought of where you could legitimately have it. Some of the disaggregated argument is that you can have, you don't need the full super fast network between the front ends, the prefill servers and the decode, because you're transferring KV cache and there are data center networks fast enough to do that. On premise, I think it's much more nuanced. I'd love to hear those use cases.
Yeah, so I mean, an example, I do have some customers who have like this heterogeneous architecture and like kind of creating this GPU farm with different kind of accelerators. So I mean, if you need more details on that, happy to provide it.
We'd love to take use cases. I think the point of this is if you have a use case and it doesn't solve, clarifying the use case, clarifying what it would need and why. That's what everybody's sharing their use cases is why we're doing that.
Great, thank you.
Yeah, I mean, the point here is like you're absolutely right. Like all cloud providers had different types of GPUs, but the point here is that for a single replica, doing tensor parallelism across nodes requires high-speed networking, and it is going to be unlikely feasible that this will work, or practical that this will work across heterogeneous nodes or GPUs. Not just because of like network latency, but also differences in flops and memory and etc. Because one of them is going to be a laggard and will make the whole group run slower.
Yeah, if there's heterogeneous compute, and I think like again, like Abdullah and I, we've got the cloud perspective and we're focused on large language model inference, and that's the dimension that we're pushing here. That's a little monomaniacal. General, like if there are other compute problems like in simulation where you're actually talking about not kind of this like really simple LLM style distribution where it's just about speeds and memory size, that would be very useful to know.
Jashin, do you want to comment on the networking that you folks have?
Yes. I think the granularity is a little bit different on cloud and on-prem. So we are on-prem users, right? And we have in some of the cluster we have big pod and the mini pod, which is a network the term corresponding to the level 3 and level 2 switch. And for those machines under the mini pod, within the mini pod, they have all the RDMA connectivities. So I think it maps to the accelerator island concept here. Sometimes I think I noticed in different cloud providers, they may not disclose that many information. They probably use a placement group or just AZ level instead. Yeah, that's a short comment on the on-prem scenario.
Yeah, the assumption is that the infrastructure needs to bubble up its topology as labels on the nodes, and using that we can map those groupings into those accelerator islands. So this is the last slide that I had, but I'm not sure how familiar the group is with disaggregated serving. I have one because I discussed this with Jashin before. With disaggregated serving, can just quickly give some background. With LLM serving, you have these two phases when we process a request. You have what's called a prefill and a decode. Or context processing. So in the prefill phase, you process the initial context that you have in the request. For example, the question, right? And then in the decode, you start to generate the tokens one by one. And the research community identified that those two have different compute characteristics. One is memory bound, the other one is more compute bound. And they identified that you could use different machines for each phase, and so you can think of it as back end and front end. Front end is your prefill, and your back end is the decode. But because you need to communicate what, Clayton mentioned, which is the KV cache, basically the state between the prefill and decode, you'll still need high performance networking between the two. Not necessarily as fast as ICI or NVLink, but at least probably within the same rack. But the point here is that the prefill and decode, those are running different, the containers are running different roles. So with LWS here, assume that your prefill and decode is a single pod, not a group of pods. Basically, the model is not that large. You don't really need to split it between nodes, but you still want to basically split the compute into two phases. Think of it as pipeline parallelism. With LWS, you can still do that if the prefill and decode are running on the same hardware, because here we're assuming that the workers are going to have the same template, and so by design they're going to have to request the same number of GPUs and land in the same on the same nodes. And so you can still set that up using LWS, where you can say, for example, your group size is 2, the leader is doing the prefill, and the extra worker is running the decode. So this is one case. The other case is where, okay, as I mentioned, those two phases, they have different compute characteristics, and you might actually run them different hardware. Like the decode, you can run it on a cheaper hardware, for example. You can set that up as well with LWS by running 2 LWS replicas. And you would want that if, again, your model is so large such that even just the prefill itself is distributed and multi-host, and the decode as well. I'm not sure if I'm being clear enough, but there are multiple combinations and advanced, I think, setups that you can still have with LWS to support not just tensor parallelism cases, but also forms of pipeline parallelism, specifically disaggregated serving. I'm wondering, like, it's hard to make, like, to create any polls here, but I would love to hear if anybody on this call that is trying to run or have some form of multi-host deployment, or is this so niche that it's still not mainstream and it's not available, like, you know, it's not a problem for the general community yet?
Right. Yeah. Based on my understanding, I think that besides the disaggregation case, I think the probably one easier case is the TP. Most of the people probably won't have the need to deploy that large models across like cross node. So I think, which means the like over 8 GPUs, right? I think it is a pattern, but I'm thinking like probably not that many users will do that way. Yeah. But for the disaggregation case, I have some comments because my company is working on this actively in this area. We do see some good performance like doing the after doing the evaluation, and the KV transfer with the 400 Gbps like network shows very promising result, and the KV transfer divided by the preview time is pretty low, which means the network overhead is kind of low. Even we use the VPC network, I think it just take like I think it depends on the TP numbers. It takes like 20 to 40. VPC is not that good, but RDMA based is pretty fast. So we think this is the yeah, this will become the like kind of a de facto in pretty soon. Yeah.
Do you plan to use different hardware for prefill and decode, or you're still not there?
No, I think from yeah, on our side we still use the same like GPUs, but we adjust the batch size and use the different ratios. And in the paper, I think a lot of like paper setup mentioned like H100 and 800. To us, I feel we like more on adjusting the batch size for different roles. Yeah, that's a different setup. And the other different, I think the other practice is I think the paper design, the machine pool is hard to implement because there's a lot of like load balancing stuff or service discovery need to be done from like prompt workers to decode workers. So instead we just do like pair-to-pair mappings. For example, in this case, like the node with index 1 always to talk to another like node group with index 1. So it's kind of, yeah, if we think one group represent prompt, the other one represent workers. Yeah, I mean, we use such like a simple mapping mechanism and fix the ratio to simplify the problem as a start.
I just want to mention that we've also have a feature within LWS where you see this group, you're able also to subgroup it so that you present those, like, you know, prefill and decode cases where each, like the prefill and decode is multi-node as well. So in this case, you could, like, you only have 4 here, but like you can divide them into 2 subgroups of 2. Like subgroup 1 is going to be 0 and 1, and the subgroup 2 is 2 and 3. And then you will get those, like, you know, second level of indices subgroup local index 0, subgroup local index 1, and this one is going to get subgroup local index 0, 1, and then and then you're able, again, like with because you have those stable DNS records, we're able to map them as well. But again, this restricts you in a way where you always have to have the same hardware for the prefill and decode. But again, like if
you have to have the same hardware now.
Yeah.
There's nothing like, so with DRA, in theory, you'd be able to specify preferences on each spec that gets you a set of hardware. What I don't think we have any mechanism for is guaranteeing consistency of hardware within a subset of the group. And that would definitely require some thought. And honestly, nobody's really asked for it yet. So I think that's why, I emphasize let's get the use cases. A lot of the homogeneous use cases the cloud users see, because it's people rapidly scaling and trying out these new workloads, whereas people on premise and existing environments have more of a mishmash of hardware. They might be building, they may make different decisions. We don't want to get locked into one mindset. I was going to ask, so another use case that we haven't talked about for this actually is multi-model, multi-application stuff. And Ravi brought that up a little bit, but for instance, in Ray, it's very easy to, one of the advantages of Ray is that for Ray serving, you can actually specify, 10 functions, talk about how they interconnect, and Ray figures out the details. When Abdullah and I have talked about this in the past, we'd be like, what we are effectively doing with the architecture shown on screen is you're creating a little mini Ray cluster where you've decided what the components are going to be and you could absolutely support multi-models, and some of those use cases where you do need some of that subgrouping could be solved by Ray in this case, because Ray will have a static set. Ray has some scheduling primitives. That came up in the Ray serve one a little bit, and I wasn't there for that, but I was reading the notes. I actually don't know how many people today are doing multi-model applications, running it in production, where this would actually make operational, like a point of integration between Ray and Cube, especially, where this actually might be operationally better for them because they don't have to go spin up all the little clusters and they don't have the single failure domain of the large cluster.
Actually, I'm trying to understand the question here. Like using Ray, even we do some complex like deployment graph, right? So it doesn't raise the requirements on the resource layer, because those are orchestrated by the Ray, and the unit is the actor itself, right? In that case, I think the deployment graph is I think doesn't introduce a new challenge or requirements on the resource layer. That's how I think currently like Kubernetes works. Do you mean if LWS can support such like multi-model composition case natively, or still?
I mean, it effectively does, but what it is offering here, what this example is showing is that is a Ray cluster on screen for that one replica.
Sure.
And that contains only the deployment graph for a multi-host inference. But it would be very reasonable to say, well, you could define your graph, figure out what the resource requirements of the minimum set of that graph, like when fixed ratios are in play, like, you want 2 of the front, 1 of the back, or the 2 front end, 1 back end, the back end is half the resources of another. Okay, here's how you would turn that into physical hardware. If you were operationally, there are kind of some advantages, because what you could do is auto scale that unit, and you don't have to worry about correlated failures, right? Like if one of your backend units dies, do you want to represent that multi-model application as a set of replicas or as a set of microservices? In either case, you could imagine it as 1 Ray cluster for everything, 1 Ray cluster for the front end model, 1 Ray cluster for the mid-level. Each of those is a microservice. Or you could say, in this scenario, you can deal with it as groups of replicas, so that you have, n+1 or whatever failure semantics you want. So I don't know how many people have use cases like that, but I think we want to know, because that would also be something we use to influence the design of LWS.
Right. Yeah, I think I can share some I think design discussion we had internally. We think for the multi-host like orchestration, we split the problem into two sub-problems. One is similar like a leader worker set does. So the concentration is doing the role orchestration inside the group, and then at the group level, the behavior will be similar to deployment. And we have another direction is doing the multi-deploy. We call it multi-deployment. So multi-deployment have the role have the different deployment at the top level. So inside the different deployment, it has like a replica concepts. So that's totally different from the current design. So the use case is exactly for those multi-model composition, like in, for example, in TikTok, like speech, when user like show the video or talk to the app or something, there's the complex pipeline, and that pipeline consists of different like models. Actually, they are not large models. Sometimes they are like 1 billion parameter models. There's a complex deployment graph, and has a ensemble or like chaining or dynamic selection or dispatching, like those orchestration primitives. So in that case, their challenge is how to manage this pipeline efficiently. In the past, they have the separate applications and let's say doing the upgrade one by one, but that's not a very I think efficient way. So if they like to have some upgraded primitives for the whole pipeline, that's a big challenge. So we use the multi-deployment to solve that kind of problem.
Let me put this in terms that I would use. So it sounds like what you're saying is when the ownership and the update lifecycle or the development lifecycle of each of the components varies, you find strong separation in their mechanisms of rollout valuable. When they're more of a single team deploying something complex, there's value in the composite, or the as you call it, like the shoot, I'm sorry, I forgot the name of it. We should really write terminology down.
yeah. Right. I think, yeah, in that case, it's the similar like managing different applications in one under one umbrella, and probably coordinate on the upgrade expenses. And normally they have a kind of I would say like entry point. So the entry point plays a role of the orchestration, and like a micro service like a request like chain. Yeah.
And maybe one more use case just to like see if anybody else here. So, or two more use cases. So one that I think this could be relevant for is, while a lot of historical computation was simulation and batch in like, what would have been early users of accelerated hardware was more like, modeling, big complex simulations. They tend to have more of a batch role. But in the HPC community, there are elements that are both batch and serving within many of those kinds of workloads. I do think this kind of aligns with some of the cases where you could imagine you're definitely using more resources than a single accelerator or a single node provides. I think LLM is one of the first cases that I've seen where that happens, but if others in the HPC side, or if this is like a general call for people in this working group or people who know people, if there's HPC use cases that map to this pattern, that would be useful to know. And then one other would be we're hypothesizing, and this gets to Abdullah's point about maybe we're a little early on this, and this is still a little niche. Looking at future LLM developments. LLMs today are very simple. MOEs are kind of like the first example where you have some more complex internal structure. I think there's a little bit of looking forward We just want to at least be thinking about or looking for signs of as models get more complex internally. So disaggregated is the first example, but you could easily imagine, you know, maybe like a set of LLM subcomponents that are trained individually, but form a composite because it's very expensive to train the whole thing together. But if you have multiple models working in close proximity, some of them may have different roles. This isn't perfectly flexible to that either, but that would be another, like, you know, when do today's multi-model use cases start looking like multi-LLM models is another, I think, input that we're looking for from folks. If they think they won't hit it this year or next year, that's a different story than if, you know, people are starting to layer or group multiple models together and then run, you know, training and model glue layers that stitch them together. We're kind of looking for signs for that and as an input. Yeah, speculative decoding, John, and that's an interesting one because the speculative decoding model is tiny generally, but if it stops being tiny or there's something more complex than speculative decoding, we're also looking for those things, absolutely. I was calling speculative decoding an example of a sidecar model where it's really derived from the primary and it sits alongside it because you typically run on the same accelerator in the slack capacity. And so if people have examples of slack capacity or sidecar models or compositions of LLMs, that would be very useful.
All right, that's all the slides I have. Yashin, back to you.
Oh, great. Yeah, anyone have further questions? Yeah, we're almost, I think, running out of time. Yeah, if no further questions, I think we can conclude the session here. Thanks, Abdullah, for the sharing again, and thank you for everyone for joining the meeting. And we will update the recording shortly. Yeah. Bye.
Thank you.